All right, welcome everybody. Here we are already at the May meeting of the Royal Astronomical Society of Canada. My name is Brian McCullough. I'm the meeting chair. Our president, Chuck O'Dale, is fishing around in the bags like a raccoon in a garbage can right here. He can't hear the microphone back there, so feel free to chuckle. At working the controls, working the computer is the other half of this team that puts the program together, apart from the presenters who are giving us the material, Chris Tarrant. So last night, he and I, usually the night before, we put the program together, and we have a blast doing it. So it wasn't the free beer that keeps you happy, is it?
That helps.
Oh, it helps. Okay. All right. All right, here we go.
Free beer tomorrow.
So tonight, we have one main speaker tonight, Simon Hanmer, all right, geologist, speaking on the impact structures of the outer moons of the solar system.
Right.
And he's going to, we've got a bunch of announcements and things to start off with, and once he gets, Simon gets rolling, and that'll lead us right up to the break, where we're going to do some door prizes and get into our observations and observing challenges. All right. Has anybody had a chance to get out and do any visual observing or anything over the internet, anything like that? Yeah?
I looked up at the sky.
You looked up at the sky? I looked up at the sky 2 days ago, and I was looking at these pellets coming down. I thought, this can't be right. This can't be right.
That's a near-Earth nebula.
Yeah, near-Earth nebula. That's a good way to put it. All right, we'll go to the next one there, Chris, please. First off, I'm very happy to announce that our good friend Paul Commission is back with us for the first time in ages. Paul, welcome back. So Paul's just sitting here right up front, and when we get into the observing challenges later on, we've got a nice observing challenge from Attila Danko, and we also have one from one of Paul's picks again for this evening. Okay. All right. Big news here. The one of the highest awards that you can win in the Royal Astronomical Society of Canada is the Ken Chilton Prize, and the winners for 2008 are the team of the Tim Puckett, the Puckett Supernova Search Program. So it's a team of people that are scanning the sky, taking photographs, taking images, and they have a team of people that take the images and put them on their computers, and they have special software to do, just like Clyde Tombaugh did back in 1930 when he was hunting for Pluto. He took photographic plates of the sky. When he was hunting for Pluto, he would take an image of an area of the sky, and that would be on a glass plate. It would get developed on a glass plate. And then several nights later, he would take another image of the same piece of the sky. And then he'd put these two plates under something called a blink comparator microscope. And what would happen is he could throw a lever back and forth, and what would happen is you'd get the image of one, then the other, then the one, then the other. And when you do that, what happens is the star images, since they're all in the same position, if you just put your two hands together, they marry up just like that. If there happened to be an asteroid in plate 1 and it was in a slightly different position on plate 2, it would hop back and forth, bing, 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 right? And in this way, he actually discovered a number of comets, asteroids, but of course the big discovery was the non-planet Pluto. The dwarf planet, the minor sub-dwarf. I'm getting into Lord of the Rings stuff here.
Object.
Not
Yes.
quite a real planet.
And I remember at the time, in 1989, when he visited the Royal Astronomical Society of Canada, he went around doing a speaking tour across the country. And this is just after I had joined the RASC in '89. And he was speaking to us at the old NRC building down on Sussex Drive there. Patrick, were you there for that one? Patrick Laffey, were you were there for that one, I think? Yeah. And this little guy came in from Arizona, all hunched over, and he had his Western kind of, well, they call it a necktie, and down in the Southwest, it's this little piece of string with some kind of silver thing hanging off it. He came in and he described what his search was like. 16, I guess it must have been 59 years earlier. Right? He was just a 24-year-old photographic assistant. That's how he got hired on at the Flagstaff Observatory, Lowell Observatory in Flagstaff, Arizona. And how he got hired on was on the strength of his astronomical drawings. He'd be out in his farmer's field, in his daddy's field, with his telescope that he had made, looking at the planets, sketching the planets, and he sent these down to Percival Lowell down at Flagstaff Observatory. Of course, that got passed on to, was it VM Slipher?
Yeah.
Right, that's who was the sort of the chief astronomer there at the time.
He was the director.
Oh, he was the director. Slipher was the director, okay.
Yeah, Lowell was dead by then.
Yeah. Oh, who?
Lowell was dead. But
Oh, okay. So he looked at these drawings from from this young fellow up in Kansas, I think it was, and invited him down to work as a photographic assistant, and he secured in his work at Flagstaff, he secured enough of a reputation for the observatory that they then were able to send him off to university later on, so he completed his education that way. But he described that time when he found Pluto. Because remember, the planets were known up to Uranus, up to Neptune. The way they knew Neptune was there, of course, was after Uranus had been discovered. They said, well, okay, let's have a look at how our solar system's working. There are perturbations in the orbit of Uranus, little bumps as it's going around in its orbit. What's causing the little variations, these perturbations in its orbit? There must be, and they figured it out mathematically, there must be a mass of so much lying off in a certain direction at a certain distance to cause that kind of a perturbation in Uranus's orbit. And there's another story about that, and I'm hoping maybe one of these days, maybe Carmen, that might be a nice little package one you might want to do for us sometime, just on what happened there. And why that discovery wasn't secured for Great Britain, the discovery of Neptune, and sort of within the hour, once all the data was passed across to an observatory where they could make visual observations, Neptune was picked up just like that. But then they looked at all this and said, seem to be perturbations still. There must be some other trans-Neptunian object out there. The search for planet X was on again. So here's Clyde Tombaugh, 24 years old, cranking off these glass plates, blinking them, blink, 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 back and forth. And he said, and then, and he says, and there it was. He was right looking around the star Delta Geminorum, and he said, he looked at the plates, he could see this object moving, and he knew by the amount it had traveled against the background stars in 3 or 4 days that it had to be a trans-Neptunian object. And he said, I knew right away it was the object, it was Planet X. And he said, for 45 minutes, I was the only person in the world who knew where Planet X was. And then I had to tell my boss. What these guys are doing is very similar. They're following in his footsteps, or in his blink steps, if you want. So they're using software now to pull up a blink comparator software program on their computers. They have an image and a later image. Blink, 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 blink. They're looking for the objects that are hopping back and forth. Oh, look at this. We have a star field. The star fields marry up again, but bang, what's this? One more star has appeared. Supernova. A star that is suddenly brightened, possibly a millionfold in a very short period of time. That's what they're picking up. So they've actually done quite a bit of work. They've accomplished great things with this. This is the team. We've highlighted the people from the Ottawa Centre, Deborah Saravolo, Lou Cox, Ajay Siegel, who lives out on the west coast of the United States, Jennifer Tigner, Deborah's daughter, of Victoria and Ottawa, Peter Saravolo, and Doug George. They are getting the Ken Chilton Prize at the General Assembly of the Royal Astronomical Society of Canada in about a month, at the end of June. So. All right, let's do some little interaction here. I was just poking around the web. I don't normally poke around the web. I think I was looking for something else, and I saw this, and I thought, oh, that's interesting, which is the way things usually happen.
Well, normally you get the porn site when you're not trying.
Oh, yeah. All right.
It's embarrassing at times.
So here's the Hubble site. Okay, here's Hubble site. I think if you Google Hubble site, you'll find it. And what I found was all these images, these posters of interacting galaxies. Chris, I don't know if you can pull any of those up.
Sure.
Click on something there. It's great being able to go online. All right, so you can get these quite high quality images off. So if you're doing some study of interacting galaxies, and they have all kinds of stuff there. I mean, you can lose yourself for a lifetime. All right, what else have we got? Maybe one of those posters, please. Does that go bigger or?
Yeah.
Cool.
Nice.
And what happens if you run your clicker over any one of those? Does it do anything?
No, it's just posting.
Oh, it's just a poster. Okay, so it's just a one image. But all the images that were there, like we just saw that one, all the images that are there are available as individual images. So something you might want to go and play with. Has anybody seen interacting galaxies?
Not in real time.
Not in real time? Yeah?
Though I'd like to.
Yeah. Well, of course, the Milky Way is a galaxy that's interacting with other galaxies right now because there are a number of dwarf galaxies. Leo Minor dwarf galaxy, there's one in Sculptor. There's all kinds of these little things that there were companion galaxies to our great Milky Way, and they're being absorbed by the Milky Way. And the way they find some of these is they look at the way some of the stars are moving through space, and they find out actually there's a contiguous body of stars that we see in our background stars of our own Milky Way that all seem to have a certain direction, seem to have a certain age to them. That's a good clue that was a companion galaxy that's now being cannibalized by the Milky Way. You had a question, yes?
Yeah, Brian, I was going to say the other neat thing about that website is they have some very large files for some of those images. And if you download them, take them to like a custom printer. Like Peter Jedicke on his wall at Fanshawe College in London has a 30 by 40 inch print of one of these galaxy shots. And they're free. You can download them, have them printed, and you've got astro art.
Okay, so what he's saying is you can download these high-res images of these galaxies and print them off, and you're going to end up with superior reproduction on them.
And perfectly legal.
And perfectly legal. Yeah.
No, it is, quite seriously.
All right, so good spot to go.
So, into our monthly trivia question. The rules are, think about it, Googling, no fair, and see me on the break, and the correct answer will get a the prize. And tonight's prize is one of the best science fiction books I've ever read by Gregory Benford, The Sunborn it's called. And I've had some very good reviews on this one. So, the question is, of course, what is the astronomical significance of this time of the year? May the 1 to 5. Think about it, talk to me at the break, and if you get the right answer, this one. And if there's more than one right answer, then I will ask some more questions. And at this point, I'm going to introduce to you Eric Kujala. He's the person that's doing the videotaping of our meetings, and he has a few words to say. Eric.
Thanks, Chuck. Hi, everyone. I've started editing these videos, and I tell you, I really enjoy doing it, and I get so much more out of seeing and hearing from the presentations again, and I'd like to encourage you to use these. I also realize that as these videos are made, that the production value should improve over time. So I'm putting out a challenge. If anyone has any comments or things that should be done for the video, please let me know. I'm on the members list, the email list. That includes what the cover looks like, what the DVD label looks like, or anything in the video that you think should be done differently. Also, I'd like to know who here has a Blu-ray DVD player? Anyone? 1, 2. Okay, all right. Well, Blu-ray is going to be the norm pretty soon, so we're going to start publishing on Blu-ray as well. Thank you.
Cool. Thanks, Eric.
Hi, just a few quick items regarding the observatory, FLO. We are due for the normal spring training course for those people that want to get up to speed on using the FLO scope and general facility. I will leave a sign-up sheet on the stage here during the break or after the meeting. Leave your name, telephone number, and email address if you have one. Be particularly careful in putting down the email address so I can decipher it. The plan is for the course to run next Saturday, May the 10th, starting about 1:30. It's about 2 hours long. It's an outside course, so rain, or rather the lack of it, is important. Rain date is probably the Saturday after, so we'll see how it pans out. So anyone interested in getting up to speed on the FLO facility, sign up. The Second point regarding FLO, key holders from last year. If you want to renew, I'm available at the break or after the meeting. The usual arrangements apply. Return the key and $35 fee for the new year. Okay, that's it. Thank you.
Okay, folks. Not a tremendous amount as usual. We do have a new nova. New nova. Boy, there's a new star. Yeah, there we go. Nova in Sagittarius. This is not quite at naked eye brilliance, but it's brightening at about 0.7 magnitudes a week. So they're expecting it should become naked eye quite soon. So it is, at last I checked, it was sitting around 8th to 7th magnitude. So it should be a good binocular target. So right next to the teapot where it will be behind your neighbor's chimney, where you will not be able to see it, but, you know, you can give it a shot anyway. This is kind of fun, Mars, the Moon, and the Beehive, and you'll notice I have this for International Astronomy Day, so this will be kind of a fun thing just in the early evening, so there will be something even in the early parts of the night. I suspect most people are going to find Mars remarkably underwhelming, though anybody who's here will probably be asked for it, but certainly this will be something kind of nice just to, you know, a good Larry light bulb ain't this cool for visitors, and they always kind of like it. They'll probably see 2 bees in the Beehive, but they always like the moon anyway. So that's anyway something for next Saturday that we won't be able to see because of the inevitable cloud cover. Moving right along. This is really quite cool. Mars is really, it's in its stage in its orbit right now where it's apparently zipping right along. And I really was quite impressed with the simulation on this one. Over the course of a few hours, the motion of Mars across the Beehive is really quite noticeable. So this should be quite fun. I'm looking forward to this. So I'm going to attempt to collect some chickens to sacrifice them for that evening and attempt to actually see this. And we did a little animation for this as well. So this is a little bit faster than real time, as you may have gathered.
I hope so.
Yes, exactly. This is the, well, in honor of the death of the creator of LSD, this is the LSD version. Hey man, my time sense is really cool. But so there you go. This actually, if you simulate it in real time, even over a few minutes, the motion is quite noticeable. So I'm really kind of hoping for this. And you can see it's simulating the wisps of clouds. So this is really very realistic.
Except there'll be more.
Except there'll be more of them, yeah. All right, so it's, yes.
You've got the star eclipsing the planet.
Details. It's a contrast effect.
Mars isn't moving at all. It's the stars that are moving.
That's right, yes. That's what Galileo said. And they forgave him for it 400 years later. Anyway, moving right along. So just in case our newcomers, you can find the Beehive. And you've got happy little Saturn right there, where it's carefully hidden by the line. That's okay. This doesn't happen outside, folks. Don't worry about it. You actually will be able to see Saturn, the line. Actually, this is the rings. These are the, never mind, shut up, Cole. So anyway, it's disgustingly easy to find the Beehive because it's halfway between 2 nice bright stars. And this star you won't see anyway, so don't worry about it. But the Beehive, and if you move ahead, I put a little circle. Unfortunately, it's very hard to see the circle outside. I should have put that in green so it would simulate a green laser pointer.
Are you colorblind?
No, I said I should have put it in green, you twit. Anyway, there you go,
I said
folks.
you couldn't see it. Or in the sky, you meant.
Earthling, you're becoming very, very irritating. Okay, guys, there you go. Have some fun with the sky this month. Oh, I forgot. Oh, whoops. One more time. Jeez.
Notice I said nothing.
Yes, I know that. Yeah, that's all right. Oh, yeah, we have a full moon this month. Gee, who'd have thunk we have a full moon this month? This is the smallest full moon. This is the smallest full moon this year. So it's really kind of cool. That's right, I did a few more slides. You asked me to put them in, and oh, never mind, forget it, too. It's just my feeble-mindedness that's coming out. So here we have the difference between the full moon in May, full moon in December, and it's quite a difference in sizes because it's just a question of whether we're at apogee or perigee, depending on when the full moon comes around. So it's quite a difference in size. It's really quite impressive. You can really notice it yourself if you take some photographs because your field of view will be fixed. So it's really quite fun. I've got a couple of pictures like that.
Orientation has changed slightly.
Oh, geez, that's why they made Photoshop. Moving right along. There, just a little picture of what we've got. Last time we did this, Brian reminded me to remind people of what an apogee was. It's actually a very expensive camera, but yeah, I know. Get the hook. But it's basically just the furthest distance from the Earth, and you can see it's quite a lopsided system. So there's quite a difference. And then one last item here, just as a point, it's a fun little system because the center of mass between the Earth and the Moon is actually nicely inside the Earth. So it's a funky little system. This is. We had a fundamentally earth-shattering kaboom. Literally earth-shattering kaboom when we actually made the moon, so it seems. So anyway, there's your piece of utterly useless trivia that you really won't give a hoot about for this evening. And now I'm pretty sure I am finished unless I've lost a few more brain cells between now and then.
You've gone black.
Thank you. Well, you know, as a geologist, I can tell you that although Chuck may think rocks rule, that only applies in the inner part of the solar system. What we're going to look at is the outer part of the solar system. We're all familiar with the classical impact structures on the moon and the rocky planets. You know, through our telescopes, we can observe the geometries of impact structures or the giant impact basins on the moon. And through books and through the internet, we've got a pretty good idea of what these features look like on Mercury and on Mars. Next one, please, Chris. But what happens when a comet, an asteroid, or a large meteor impacts the surface of an icy moon, such as those in the orbits of the outer planets? What do those impact structures look like, and how do they compare with those preserved on the rocky planets? So let's start with a look at the old battered surface of Callisto, one of Jupiter's ice moons. Now, because Callisto is essentially cold and dead, or at least it's supposed to be, the impact features that have accumulated since the beginning of the solar system are still beautifully preserved. Next one, please, Chris. Now, Valhalla, the palace of the Norse gods. This is a thousands of kilometer wide multi-ring impact basin. Let's see if I can actually make this work. Yes, there we go. So all these rings here, these are the multiple rings of the Valhalla impact basin. And superficially, it's very much like the Orientali basin on Earth's moon. It's difficult for us to see from Earth, but with the wobble of the moon, the libration, we can sometimes see parts of it. It's also rather similar to the flooded equivalent of these impact basins, which we call the Imbrium Basin on the moon, and that we can see. However, Callisto is made of ice, and ice does not have the same strength characteristics as rock. So it's not surprising to see significant differences. Next one, please, Chris. Now, look at how shallow this central depression is at Valhalla. This is certainly not one of Chuck O'Dale's big holes in the ground. Press forward twice, Chris. That way we get rid of that circle, and we'll see what we get next. There we go. All right, so now let's look at the number of concentric ridges that surround the impact site. It's at least double, if not more, the number for the best lunar examples. In addition, there are no rays of ejecta. There are no radial rays of ejecta coming out from the impact site. So everything points to something relatively soft. In other words, this impact was more of a splat than an explosive impact. And that would also explain the low relief of these concentric ridges and the shallow central cavity. In other words, the initial impact structure, the hole, if you will, would have collapsed rather like melting ice cream. Now, bear that analogy in mind, because I'll come back to that one a number of times. So the next one, please, Chris. Okay, so here we've got a detail of the previous image. These concentric ridges, although they're low, they do have some topographic relief, though as you can see here, enough relief to cast a good shadow when the sun's low on the horizon. Next one, please. But here's the surprise. In addition to these 10 or so principal concentric ridges or scarps that we could see in the previous photograph, there are many minor low-relief scarps in between them, as indicated by the red box. And this is another feature that we just don't see on the Moon or on Mercury. Next one, please, Chris. So here's another close-up on Valhalla. Valhalla is an old impact basin. Next one, please. Next one, please, Chris. Thank you. And as you can see, as the box illustrates here, we can tell that it's old because of the density of small impact craters that have scarred the concentric ridges of the basin itself. You can see these small impact features there everywhere. But this is not the oldest part of Callisto's icy surface. Other parts of the Moon have even higher impact crater densities, and that means that they're even older. Next one, please. Now, I've shown you this image of impact craters on Callisto in a previous talk. The impact craters are pretty obvious, and they show some similar features to those of the rocky planets. For example, the larger craters have central peaks, like this one here. There's a central peak, just like you'd expect to see on Earth's moon. But there's something a bit odd about this battered icy surface. You notice how the walls of this crater here, they seem to be eaten away, and so do these over here, and even these ones over here. Next one, please, Chris. And if we focus on that large crater in the red box, you can see that the walls even seem to have moved around. In other words, they've actually slid down into the crater pit. Now, for physical reasons that I don't yet understand, I've looked on the internet, but I don't see anybody directly explaining this to me. The ice of Callisto's surface is capable of crumbling and moving around like sand, which is kind of strange behavior for ice. So the next one, please, Chris. Now, Europa is another one of Jupiter's ice moons, but this is one with a very young and very active surface, as we can tell from the very low number of preserved impact craters. Europa is so active that it's constantly resurfacing itself, and therefore it eliminates the older impact structures. Now, even from space, it looks as smooth as a billiard ball, which is a reflection of the fact that Europa's ice is too weak to support the weight of a significant mountain chain like the Himalayas on Earth, or the ring of mountains around the Mare Imbrium on Earth's moon. Next one, please, Chris. However, comets, asteroids, and meteors do strike the surface of Europa. So what do the impact features look like in this relatively weak ice? Well, here are four classics. There's the unpronounceable Pwyll crater. That's Welsh, by the way, and you might tickle your tonsils trying to pronounce that one. The Cilix crater, that is number 2 there, which is much younger than a complex array of ridges in the icy surface of the Moon. Here you can clearly see that this crater here is cutting right across these ridges. We talked about ridges in previous talks, ridges in these icy moons. That clearly is a young feature. That's Cilix here, and this is Pwyll. Actually, there'll be a test afterwards. You all have to learn to pronounce Pwyll. The impact ring structure, Tyre, here. You notice the 20-kilometer scale bar down here? Well, it applies to all of these images. So that actually, although it's a multi-ring crater, it's not a multi-ring basin. It's a pretty small feature. It's way too small to be considered to be an impact basin. And then there's this one here, Manannan, another one that's a beautiful one to pronounce, but it's as difficult to pronounce as it is to see. Frankly, if I weren't pointing it out to you, you might not even be able to see it in that image. What all of these impact structures share in common is, again, very low topographic relief, very shallow crater floors, and very low crater walls. So again, this is a function of the inability of the relatively weak ice of the Moon's surface to resist the pressures that would be generated by major differences in topography. If you have a hole, a deep hole, kilometers deep, with walls which themselves may actually be kilometers higher than the average surface of the Moon's surface, you generate a pressure gradient. You've got more pressure under the high walls than you have actually in the hollow which forms the floor, if you will, of the crater. And so therefore you need a strong material to resist the tendency to flow. And because this is weak material, the weak ice cannot actually support the pressures generated by those major differences in topography. Next one, please, Chris. Okay, here's the multi-ring structured tire placed in regional context. And there again, there's a 40-kilometer scale bar here, and there is tire. Not that big. Only 40 kilometers across, and you can easily see how shallow it is. Technically, this is referred to as a macula. Macula literally means a stain in Latin. And the lack of rays of ejecta is particularly obvious. Now, on Earth's moon, this multi-ring geometry is only found in the giant impact basins. But a structure of this size is clearly just a modest-sized impact crater. Now, this is not the youngest structure in this image. As you can clearly see, it's cut by long ridges of the kind we've already talked about in previous talks. There's a long ridge cutting right across that structure there, and there's another long ridge cutting across the multiple ridges. Now, next one, please, Chris. Now, this is a false color version of the same structure. In other words, NASA has basically put this one through Photoshop and added some colors to it. It looks like a watermark in Europa's surface ice, which is technically referred to as a palimpsest. I spelled it out for you there. The only reason I'm giving you these names here is in case you sort of read this stuff yourself and wonder, what the hell's a palimpsest? That's what this means. It basically refers to it looking like a watermark. Now, the accepted interpretation of these low-relief impact features is that they formed in soft, perhaps relatively warm, and perhaps relatively thin ice. Now, hold that thought, relatively warm and relatively thin ice, because we're going to come back to that in just a minute. Next one, please, Chris. Now, tire is not unique. Next one, please, Chris. This is another macula on Europa, and here the box here actually gets you into the core of it. You can see the concentric features here, the concentric ridges. There are multiple ones here, 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 here. And this time, this is the youngest feature in the image, since it actually cuts all these triple band structures. You see this triple band here, made of two high ridges separated by a central valley. There's another ridge, exactly the same kind of structure. They're called triple bands. And this triple band down here is clearly cut and truncated by one of these concentric ridges related to this macula. Next one, please, Chris. Here's the unpronounceable Pwilch. I do mean it. There will actually be a test at the end. The impact structure, the impact crater itself, is actually this. That little black dot there is a 25-kilometer wide dot in the middle of this white splash zone. Now, in contrast to the previous structures, this one has an enormous set of ejecta rays, which are thousands of kilometers in length. Now, look at the scale bar here. That's 1,250 kilometers. And look at these ejecta rays coming out from this crater, which had absolutely zero relief on it. Now, because these rays cut across all the cracks in the ice ridges, then this Pwilch itself must have been a very young feature. Next one, please, Chris. Now, the question is, actually, no, can you back up one for me? There, we're back to Pwilch. Now, the question is, why? Why does this impact crater look like a classical lunar feature such as Tycho on Earth's moon? That's the attachment point of the orange, if you like, when you're looking at the full moon down in the southern part of the moon. You can see a crater there with rays which radiate out from it. That's the crater Tycho. Why does it look like a classical lunar feature here when we've just seen that other impact features on Europa are so different? One possible answer is that this impact crater formed in relatively cold and relatively thick, and therefore relatively stronger ice than the tire multi-ring structure. This sounds like a pretty good explanation until you go in a bit closer. Next one, please, Chris. And here's a close-up of the Pwilch crater itself, and you can clearly see this time around there's no topographic relief whatsoever, just like tire. So this suggests here that the ice was too soft to support a deep hole with crater walls, all of which puts us back to square one when trying to explain the ejecta rays that we just saw in the last image. So the take-home message from the surface of Europa is that impact structures in ice on that moon still remain a mystery. We still do not understand the mechanics and the behavior of impact features on this moon. Next one, please. Next one, please, Chris. Thanks. Okay. Impact structures on the surface of Jupiter's ice moon Ganymede come in two flavors, depending on whether they occur in the older, dark terrain. That's this stuff here, for example, or this stuff over here. or whether they occur in the younger, lighter colored terrain which occurs between. So you can see the lighter colored terrain in through here and around here. Now, in the older, dark terrain, the impact structures look just like those of Europa. You can see them here, here, here. There's some nice large ones. I think you can see those even from the back of the room. They look like the ones on Europa, except that they're more numerous. In other words, the larger ones are generally shallow, with very little relief, and show no ejector rays at all. But in the younger, light terrain, all the impact structures are well formed. They have deep floors, they have high walls, and they're surrounded by very obvious, splashy white rays. Look at them down there. You even get them in these smaller ones here and over here. Now, you can see those white rays even from a distance, even as in this image here. So let's go to the next one, Chris. Let's zero in on this red frame. Next one, please. So here's a detailed image of the older dark terrain with three kinds of impact features. First, there are these closely spaced, gently curved ridges that you can see through here. The ridges and grooves, and they run northwest, southeast across the photograph. And they're the remnants of a giant multi-ring impact basin similar to Callisto's Valhalla. Next, please. And the grooves have been overprinted by large impact craters, which are therefore younger than the impact basin itself. And notice how both the grooves and the larger impact craters have very subdued topographic relief. So again, we ask the question, does this indicate that the impacts occurred in relatively soft ice? Hit forward again, Chris. And again. Now, the third kind of feature are relatively large impact craters and grooves. The relatively large impact craters and the grooves are themselves battered by smaller, younger impact craters, and these are pretty well formed. They have deep floors. There's a really nice example there and a nice example down there. They have deep floors. They have high crater walls. They even have central peaks. In other words, these are classic impact craters. These small impact craters look like they formed in relatively hard ice, but it's the same ice that these things formed in, and it looks like soft ice. So what's going on here? As you all know from shoveling your driveways, relatively warm ice is relatively soft. And if that ice gets to cool, if it gets to really freeze, then it's a lot harder to shovel. So is it possible that in this image what we're actually observing is direct evidence for the progressive cooling and stiffening and strengthening of the surface of Ganymede with time? In other words, there's the initial impact by the multi-ring basin with low relief ridges, which then itself is impacted by, is peppered with impact craters into still soft ice, and they therefore have a low relief. Through time, the ice cools and gets even harder still, and so now the youngest impact craters have that classic crater morphology to them. Next one, please, Chris. Now let's take a close-up at one of Ganymede's impact craters in soft ice, and this is one called Neith, which is spelt down here, Neith. And this one here is the one we're looking at. You see the size of it, 150 kilometers. Not only is Neith's topographic relief very subdued, it's inverted. It's not a hole, it's a hill. Here's the outer limit. Next one, please, Chris. There's the outer limit of the crater. And that crater, that outer limit is about 160 kilometers across in this very shallow crater. Press forward twice again, please, Chris. There we go. Closer to the center of the crater is a ring of what looks like chaotic rubble. And we know that central rings, instead of central peaks, are well developed in large lunar craters. Press forward twice again, please. And here, right in the center, as I said, instead of a hole, what we've got is a hill. So what's happened here is that the walls of the initial hole that formed in this soft ice collapsed to fill in the hole, and by flowing in from all sides to the middle, the ice produced a dome at the impact site, which is therefore a positive topographic relief. Now this process of flow in soft material to fill a hole like this is known as viscous relaxation, because the pressures in the ice around the hole that I mentioned earlier are relaxed by the viscous flow of the ice back into the hole formed by the impact. And just so that you don't get the idea that this is something weird and unique to Ganymede, next one please, Chris. Here we are on Callisto. This crater is called DO. You can think of this as Bart's crater, if you like. There's the outer limits of it, and here's the scale bar of 25 kilometers, so that's a good 50, 60 kilometers across there. Go forward twice, please, Chris. And here's the outer limit of the shallow crater, and there we have, there's the shallow crater, and there's the dome in the center here. So this is a relatively common phenomenon on these icy moons. Next one, please, Chris. And again. There we go. Okay. In another part of Ganymede's surface, we see a wide expanse of light, young ice, with large blocks of older ice floating in it. So here are the large blocks of dark, older ice, and they're floating in this light-colored, younger ice. Notice how the impacts in the younger ice are very different from those in the dark terrain. Just like Twilth on Europa, they're very splashy, and they have extensive white ejector rays. You can see them here beautifully. Lovely classical craters, lovely white ejector rays. Next one, please, Chris. The one exception to this is circled right here, where a splashy crater has formed in the dark ice. That was the ice that had the very shallow, low topographic relief impacts. But that simply tells me that this particular patch of dark ice is actually very thin. And what's happened is that the impact has gone right through it and has actually managed to dig into the underlying light-colored ice, which I'd suggest is perhaps stronger. This is what... Oh, next one, please, Chris. This is what the craters in the light young ice on Ganymede look like when you're in close up. They're well formed with deep floors, high crater walls, central peaks, especially in the northern one right here, and well-defined collapse structures preserved against the crater wall in the southern one. You can see them right there. This looks exactly like the kind of thing you can observe on the moon when you look through your own telescopes from your own backyards. The beautiful preservation of these classical impact crater features tells us that this young ice must have been strong like rock. And presumably, that's because it was relatively cold. Next one, please, Chris. So, can we explain all the differences between the subdued, older, and the splashy, younger impact craters on Ganymede in terms of hardening of the moon's surface ice as the temperature decreased with geological time? Well, I'm afraid we can't. And this picture here shows why. This is an impact crater chain that crosses the boundary right here between old impacted ice and less battered younger ice up here to the northwest. The crater chain was formed by an impactor that broke up into separate bodies just prior to impact. So it's one event. It's one instant in time. And notice the lack of ejector material associated with the crater chain component here in the older ice. And next one, please, Chris. But notice the splashy light-colored ejector associated with exactly the same crater chain in the younger ice right here. This is all the splashy ejector material. The craters look similar in both parts of the chain, so it's reasonable to assume that the ice was equally strong in both older and younger terrains at the instant of impact. But I have no idea how to explain the distribution of impact ejector in this image. I've thought about it, and I'm completely stumped. I cannot tell you why there's no ejector here and there's ejector there. So again, I guess the take-home message is that impact features in even this icy moon still require a lot more explanation. Next one, please, Chris. Okay, I want to end this talk with a brief look at what happens when a relatively large impactor hits a relatively small icy moon. There are, in this image here, you've got three views of the crater Odysseus. That's this whacking great thing here. This is all the same picture of these are three views of Odysseus in Saturn's relatively small ice moon Tethys. And there's a scale bar down here, about 500 kilometers, giving you an idea of just how small Tethys is and just how big Odysseus is in comparison. Now, compared with the size of the moon Tethys, Odysseus is so large that its floor actually curves with the moon's surface. So if you were standing at the foot of the crater wall, the other side of the crater would be out of sight beyond your immediate horizon. Now, the relative sizes of the moon and the impactor were such that the moon only just held together when it got hit. It's probable that icy Tethys was soft enough, as being ice, to absorb the impact rather than shattering under it. Next one, please, Chris. And finally, here's Miranda. This is the strangest moon in the entire outer solar system, and it orbits around Uranus. Again, it's a relatively small moon. You can see the scale bar here, about 500 kilometers across. Its surface comprises huge angular blocks with a strange banded terrain with very few impact craters. These are the blocks I mean. There's another big one down near there. This is the clearest one. This is the best focused. And you can see this banding in here. And there's not that much in the way of visible impact cratering there. But those blocks are surrounded by densely impacted terrain here. See the dense impacting here. And here's a close-up of the same thing. That's, in fact, this corner right here. There's the banding. And that's about, I guess that's about the edge of the block there. Am I right? No, actually, that's that white band there. So we're entirely within this block here. The impact crater distribution suggests that the banded terrain is younger because there are less impacts. But, next one please, Chris. That's now showing you where that detail there is, that box there. The internal structure of the banded terrain appears to be folded, rather like a chevron. That's the same thing as sergeant stripes. And the fold appears to be truncated at the terrain boundary. There's the fold there. And the banding seems to be cut right off right there. Geologically, that suggests that the banded terrain was folded first and then included in the surrounding terrain. And that's in apparent contradiction to the sequence deduced from the impact cratering. Now, the initial explanation when this was first observed was that, unlike Tethys, Miranda did indeed explode and shatter when it was struck by a massive object, but that its exploded components didn't separate by much. And they were able to accrete back together again to form this Frankenstein moon by gravitational attraction. Now, planetary scientists have since realized that this simply won't work, and are now suggesting that the bands in the banded terrain actually represent fractures at various angles that guided the eruption of ice volcanism, which we've talked about in previous talks, that replaced the older ice, and that the larger blocks of banded terrains are bounded by large geological faults that explain the abrupt boundaries. So these would have been fractures within these blocks here, and ice would have come up from within the moon along these cracks, multiple cracks to form the banding, and that then later geological faults through here would have actually chopped off the banding in this image. Now, I've got to tell you, this is a pretty sketchy theory, but this is the most modern thinking. But it's better than a model of an exploded and reassembled moon to explain Miranda. So I end this talk on impacts in icy moons with the case of the impact that never actually happened after all. Thanks for listening.
Anybody have any questions at all? Discussion on this for Simon? Gordon?
Yeah, on your the crater, what was it, Neat?
Yeah.
Would that not be spelled N-Y-L-L?
N-Y-L-L. No,
Or you had the other one which was what?
Oh, no. You have to listen very carefully. Hang on, let me go close to the microphone. The P-W-Y-L-L is Pwils.
Okay.
You actually have to sort of do something funny with your tongue between your teeth at the back. The only reason I know this is I did my undergraduate degree at the University of Wales. There are many other places that I went to with even more difficult pronunciations.
Any other questions? Yes, Pat?
Do we know what causes the dark terrain on Callisto?
No, but yes, do we know what causes the difference in color essentially between the dark terrains and the light terrains on various of these moons? We don't know, but we do know that ice will change its color according to a number of simple parameters. For example, grain size. You can actually see this if any of you actually go north or if you do any ice fishing. If you do ice fishing, you'll know that as you go through really good solid ice, when it's in the depths of winter, that ice is blue. And as the season begins to progress, the ice will eventually what's called candle. In other words, it'll then turn a white color and it gets dangerous to walk on, even though it's still thick. So if you have pure ice with large, clear, unaltered crystals, then it'll have a one color. If you then come along and damage it, either because you change the grain size or you fracture it with many, many fractures, it'll then change from a darker color, the darker blue, the clear blue, to a light color. That may well be what's actually happened. And frankly, the only way they're going to find out is to land.
There are similar analogies when we were doing ice reconnaissance up north. They had all kinds of classifications for ice, birdie bits, grommlins, and they did have different colors. So it might be the same.
Yeah, Pat's pointing out that those who actually work in the north, and she was referring to a tiller specifically, there is a classification of various ice types, and those different ices, and it's usually their structure that's the difference. They do have different colors. What's really happening is that the light is being refracted within the ice differently, or refracted off the ice differently according to the structure.
Are there grains in the ice?
Oh, yes.
Material? And how would the solar radiation affect that?
Oh, well, let's put it this way. It's not very warm on those planets. When I was mentioning warmer ice becoming colder, I'm talking about going from, well, something in the order of, say, minus 150 down to a couple of degrees above absolute zero. I don't think solar radiation would actually affect the crystal structure. I think it's more likely to be either some form of ongoing bombardment and a response to that, or a recrystallization.
You mean physical bomb?
Oh, yeah. That could be bombardment by dust, for example, would be enough to actually damage the ice enough so that it then recrystallizes with a much finer grain size, for example.
Oh, yeah.
Simon, this is a little off. Isn't Ganymede planetary size, really? Isn't it about as big as Mercury, I believe?
What is that?
Ganymede, the moon Ganymede.
Ganymede?
Yeah, is it not of planetary size?
It's of planetary size. It is indeed, yeah. It's about the size of Mercury. They are large moons. Chuck, you had a question?
Yes, regarding the different crater types in the same area, suggesting the ice was melted and hardened. Could that large impact have caused that ice to sort of be in a melted state with all the energy of the impact for a long period of time, causing the different stages of cratering? Or was that?
No, I doubt it, because the large impact to form the Valhalla Basin, it's quite clear that the ice nevertheless responded as a solid. If it had transformed into a liquid, then what we would have seen would probably be a large circular structure representing the initial impact, and then filled by something looking rather like the lavas which fill impact basins on the moon. In other words, there wouldn't be that internal structure, because the concentric ridges are part of the impact basin itself. They would not be there.
Brian, I think Brian was next.
Simon, can tidal forces change the crystalline structure of the ice?
If you could repeat that.
That's a good question. Can tidal forces change the crystalline structure of the ice? Yes, they could. But I'd be hard-pressed then to explain as to why is it that some of the ice is changing and some of it's not. What is clear, Chris, can we go back to the image of the first image of Ganymede?
Further back?
No, we want to go further back to the first picture of Ganymede itself as a moon. There, one more, I think it is. There we go. Here's the light-colored ice, and if you look, remember when I gave my talk on fracturing, on linears, I pointed this out. The light-colored ice has actually penetrated into the older dark-colored ice, rather like veins. Look at them going in through there. They're actually gigantic. They're tens of kilometers across and hundreds of kilometers long. That means that this light-colored ice was mobile, and it probably came up from within the moon, and as it's flowing, it wouldn't have been flowing as water, or even as water with ammonia, in other words, cleaning fluid. It was probably flowing as relatively warm ice, and as it does that, it actually starts to granulate itself. So even if it had had large crystals, those crystals would have been broken down. Paul's nodding because Paul was a metallurgist, and he knows this is exactly what happens in metals. And that's possibly part and parcel of the explanation on this moon as to why the difference in color and potentially difference in grain size.
And one more...
Yeah, I guess you didn't talk too much about the chemistry. I mean, are these all water ice moons, or, I mean, and I guess the follow-up question to that would be: has anybody tried to do like the mechanical modeling of that, just in a with small projectiles, in a frozen.
Yeah, the question is, I hadn't said much about chemistry, and is this just water ice, and has anybody done any modeling in the lab to see what would happen if you actually chucked something at equivalent ice? Now, the reason I didn't mention the chemistry is I've done that in a previous talk. If this had been water ice, then this ice would be so hard that none of the structures I'm talking to you about would actually have formed. You had to soften it up to get it to flow at all. And the theoretical chemistry says that there should be ammonia mixed in with this ice. That's why I referred to the ice actually as cleaning fluid, frozen cleaning fluid. I don't know whether people have actually done experiments specifically on this, but I'd be really surprised if they haven't. I know they did experiments to try and determine whether or not the classic craters of the rocky planets and the moon, our moon, were actually the result of volcanism versus impacts. And it was only about 40, 50 years ago that that was resolved. And in part through experiments. Some of those experiments were done in the late 19th century, by the way, and they were pretty strange contraptions. I'm sure somebody has, but I've not come across it.
I had a question. Why is this color photograph black and white and in the close-up is in color? Why is that? Is the close-up on this one in color?
Yeah, just looking there.
Oh, that's sort of a sepia tint that I think they may have added, but I think it is essential. All the untouched images I've seen are black and white.
Okay, last one.
Yeah, okay. On this shot here, Simon, and this, a question to the geologist. I mean, with the large areas of harder ice and softer ice welling up, that's reminiscent of a tectonic system. Does that apply? Does the tectonic model apply?
This is a very interesting question. This, as pointed out, this looks a bit like continents on a planet that's got a tectonic system. You remember I talked to you about plate tectonics and the idea of plates moving around and interacting with each other. If this were the case, we know from the way that plate tectonics works on the Earth, and I talked to you about this, the idea that the molten material from inside the Earth comes up in the middle of the oceans as the continents are moving away, and that the ocean floor plunges down beneath the edge of the continents as the continents are coming together. Then we should expect to see similar kinds of features to what we see on Earth. Mountains along the edges of the continents where the ocean is going down, or where collisions are occurring between blocks, or we should see volcanoes, even ice volcanoes, and I've talked to you about the existence of ice volcanoes elsewhere. We should see them in the middle, say, for example, if these two blocks were pulling apart. And so we don't see those kinds of features. This is probably, rather than horizontal movement, as in plate tectonics, this is probably vertical movement of ice from within the once warmer moon. And again, when I say warmer, I still mean minus 150 degrees centigrade.
Simon, thank you very much.
Thank you.
Thanks so much. And Simon, I think that qualifies as an observational astronomy. I've got a little token here for you. That's why I was trying to hold you back. Are the people who give observing reports get a little token? All right? That was wonderful. Thank you very much. Okay, so here we go with the trivia.
The trivia question. I had excellent answers. I had two very close answers, and one the closest answer.
And are you going to give the book away?
I'll give the book away, yes. First of all, the best answer I got, and it is a correct answer, but it wasn't what I was looking for. This was the launching of Sputnik, May Day. But that's not the answer I was looking for.
It didn't take 5 days to launch it, eh?
Didn't take 5 days.
It was launched in October.
Was it?
Yeah, October.
Oh, wrong answer. Shows you how much I know. I remember. I thought it was May. It was October, wasn't it?
Yeah, everyone knows that. October 4th,
Of course.
1957.
Anyway, the right answer. Put it on, Chris. What I'm looking for was cross quarter days. And I nobody pays attention to my presentations, because 3 years ago I explained that all to you.
I remember it well. Was there a hole in the ground?
Yeah, but it wasn't a hole in the ground. But let's see, where are we here? So that's Halloween right there. And we're here May Day. In the summer, it's 1st of August is Lammas. I'm not sure exactly what that is. And of course here, pardon me?
It's Buddhist. Llamas.
Shows you what I know.
Yeah.
Thank you.
I'm making a stupid joke. Don't worry about
Oh, llamas.
it. Llamas. Either that or it's South American. Llamas.
Jim, let him do it.
So, and this day is very, very special. I'm ex-military, and I can tell this joke because I'm ex-military. I'm ex-Navy, and we have a special day in May called Battle of Atlantic Sunday, when we won the Battle of Atlantic. The Air Force has, in September, Battle of Britain Day. And the Army has Groundhog Day.
This Sunday's Battle of the Atlantic.
It is, yeah. And this Sunday's Battle of Atlantic. So the winner I gave to Roy Wheeler, who wins the book, because he came the closest. He guessed Imbolc. How did you pronounce it, Roy? And he was right, because that was Groundhog Day name. So, Roy, you got yourself a book. Thank you very much.
All right. Okay, here we go with the observations segment of our program. This is an image that I shot sometime this year in the winter. I think it was back in February. This is the McNabb Community Center there. My son Nathan had a hockey game. There's Bridget standing there saying, will you ever hurry up and take this shot? It's freezing out here. But we can see there's a nice sun pillar coming up, and you can see the arc coming right here, and the two sundogs. All right.
You can give yourself an observing pin for that.
I've got a whole sack full of them right here. Okay. All right, now this one. Okay, listen, I have to tell you something here. We asked Bob Olson, listen, are you going to be here that you can present this slide that we've had for a while? And he says, no, he emails me back. He says, no, I'm in some place in Saskatchewan. I can't remember what the name of the place is. You know what he's doing tomorrow? Getting married. So he said he likely won't be here tonight. So being quick on the update, I said, roger that. So what Chris and I did, and Bob said, go ahead, show my stuff. But Chris and I decided we're going to show one image here. But what's interesting about this was one of the Deep Sky Challenges, all right? And it was for photographing Barnard's Loop around, that we see that hydrogen region around the constellation of Orion. But now when Bob Olson, when he went out to take this image, of course, he's doing a number of CCD shots, right? And he's stacking the images. Well, he had a couple of images he had to throw away. And this is why he's pegging this as an ode to Mike Earl. Because what's Mike Earl's claim to fame? Satellites. Satellites. Let her rip. These are the images he had to discard.
Don't start laughing yet.
And wait for the sporadic. Just wait for it. Stand by. Hey, where's that sporadic? So these are all normal satellites, right? I think we're going to see most going over the Canadian satellite. Well, we can tell. There. That's not it, but. So now, from the talk that Simon just gave us, this would be the surface of which outer moon of the solar system? Which one? Ganymede. Thank you very much.
The blunt message from Bob Olson was, who was the idiot who picked that image in that part of the sky? That object.
All right. So good on Bob. All right. Off we go to the next one. Are we? Oh, we had
reminder of a previous challenge.
Oh, that's why. Okay, thank you. Right. Last month, Attila Danko picked IC 4617 as the Deep Sky Challenge, and IC 4617, is right there.
nice green laser you have.
Yeah, nice segue, eh?
It was a nice challenge.
Yes, there we go. All right, so here we have, who knows what that is? M13, the globular cluster in Hercules. All right, and that's NGC, what is it, 6240? 6207. That's what I said, 6207. All right, so now, remembering that's the challenge, Gary? I hope you're up next.
Thanks, Brian.
Well, for those that do not know, I have a backyard observatory with a Me 12-inch LX200, and I have a Mallancam, which is a very sensitive video camera. And the great thing about the Mallancam is you can view live images on your computer screen. Well, since the long weekend that we had for Easter, I've been actually streaming over the internet through Live Yahoo or through Ustream.tv. And the challenge that Attila gave was, as said, IC 4617, it's about 15.5 magnitude galaxy. So I did have a clear night of a few nights we had this month and decided to go for it a little later on in the night. And next slide, please. Can you see the little dot right here? Wow. That's live. That's not stacked images. Well, the camera does stack, but not as if I took stacked images and then showed. This is what people saw when they were logged on over here on Live Yahoo. And in fact, Denis Legault actually has charts, and he was logged on too. He actually said that the faintest star in that, or that we were seeing that night, it was so clear, was about 17.5. And still live internet, live astronomy on the internet. It's quite cool.
How many people have seen Gary's broadcast?
I saw it once when it was not on.
Yeah.
It'll be on Monday. It'll be on Monday. I still have a personal life, I still want to stay married here, folks. Although, I say I'm going to be on. I try to be on as often as possible. In about 24 hours of broadcasting, up to about 3,000 guests that have logged on. Not physically logged on, but Yahoo does keep stats for people that actually hit the site. To log on to my website, wondersofastronomy.com, and I have two links usually through the Live Yahoo. So that was a pretty interesting challenge, and I'm pretty glad that I did see it. And I think there's one more slide. And this is also with the Mallancam. I actually took a video of the Mallancam using K3 CCD tools, such as I do with the moon, such as Mike Worth would do before he got the Luminera. And this was about maybe 10 seconds of stacked images, or images 10 seconds worth, which I had then stacked. So a pretty quick and dirty image of a distant galaxy about 12 million light years away.
Cool.
So again, on next clear night, which hopefully will be Monday night, I will be on astrocasting, as I used to call it. And I think I'm the only RESC member in Canada that's doing this thing.
Okay, that's
good. But it's not inventing the wheel, folks. It's just time given to it. So join in and onward and upward.
Clusters? Galaxies Nebula, but it stands for New General Catalog.
Prior.
All right. The IC stands for the Index Catalog, which is kind of an add-on to that. The M numbers, M13, and you saw on the next slide, or two slides hence was M64, the Black Eye Galaxy. The M stands for Messier, and it's there were 110 objects in this Messier list from the French comet hunter from the 17th century, or from the 1700s, Charles Messier. And he was, of course, Charles Messier was hunting for comets. He kept finding all these faint fuzzies in the sky, and he would look at that and he would say, "Ah, comet! Oh, c'est pas une comète." And he'd mark it down, his list of rejects, M1, right? And away it goes. So he became better known. Well, there are galaxies in his stack there, but he became better known in a sense for his list of rejects. But there it is.
I forgot to mention just one more thing.
Go ahead, Gary.
So I just forgot to mention the actual distance, estimated distance of 4617, but 500 million light years.
Wow. Holy mackerel.
Pretty far. That's cool.
Great. Paul, did you want to talk?
Thanks. Basically, well, this made the cover of Astronauts. I guess I had some influence on that.
What do you mean made the cover of Astronauts? You're the editor of Astronauts. What do you mean made the cover?
Okay.
It's coincidence.
It's just a coincidence, yes. Well, I was looking for images to put on. So I used one of my own. Also, this is sort of interesting. in Astronauts, there's a repeat from Robert Dick of an article that he wrote on these two galaxies that you can read. I think it was back from the 1970s. So it gives a little description of them. These are pretty common. They're M81 and M82. I always get the two mixed up, but M81 is so I got them in the right order. Good. And they're in the Ursa Major, the Big Bear, just sort of at the end of the nose, I guess, or near the off from the dipper part. So they're two of my favorite objects, and I took this image at FLO using my new S-Big camera. So nice, got them all on the same chip. Great, thanks.
That's great.
Yeah.
There's your little...
Thank you very much.
Thank you, Paul. Thank you. Yeah, now if we can go back up just one, please, Chris. M81, M82, as Paul was saying, of course, is just above and to the right of the bowl of the Big Dipper. Now, Pat Brown was looking at the article in Astronauts, and I think Rob Dick had said that put the distance of these as 10 million light years. And it's 7. Right, that's right. And what did you come up with?
Close to 12.
So close. So they're actually closer to 12 million light years away. All right. So, but compare this to the distance: 12 million light years here. Gary, what did you say? 500 million light years for?
Exactly, 500 million. Yes.
500 million for the IC object. All right.
Wow.
And did we have Paul's? Did we have his M101?
Later.
Oh, it's later. Okay. All right. Okay. Let's go to the next little bit. Okay, Rolf Meyer. Here comes. Has anybody been observing Saturn at all? Yes, no, yeah?
I didn't know I was coming up.
Rolf, did you
So-
discover a restaurant on Saturn?
Did you discover a restaurant on Saturn? I don't
know why.
Neither do I. Okay, just curious.
The bottom image actually was the one I took first, and I noticed that there was a white spot on it, and then subsequently there were other people who identified this white spot as well, and on the top is a color image on the 23rd showing the white spot. So there's two unusual things about this. One is that it's about 12 years too early. They occurred about 20-year intervals, and the last, well, actually since 1990 there have been a few other outbreaks, but the next one was supposed to happen around 2020. And the other thing is that this is in the southern hemisphere, and they're usually in the northern hemisphere. So, but there you go. Other people have imaged this as well. So,
okay,
that's it.
Great, thank you. I just figured out the reference to the restaurant. Somebody made a comment, did Rolf discover the first restaurant on Saturn? Of course, I didn't read the words there, White Spot, the White Spot restaurant chain.
I have no idea what that is.
We'll just ignore it. There's your... Thank you. Thanks, Rolf. Thanks, Rolf. Now, I was looking at Rolf's image when he passed it in to us, and I thought this was all very interesting, so I just had a look on I jumped onto the Cassini site. All right.
Yeah.
Now, I don't know if anybody's seen these. Now, there's a pair of images here. What they're looking at, and this is also in the, that was in Rolf's image, the southern view was up, or south was up in that. Here's a southern view of Saturn again, but what they're focusing on is this great electrical storm on the surface of, on the upper decks of Saturn. Now, what they're saying is this is the longest observed electrical storm on the surface of the planet. They've been observing it for 3 months now. So what they've done is they combined the red, green, blue spectral filters. That approximates more normal human vision on the left. And over on the right, they were trying to tease out some more details. And this is the thing. When you start working with different filters, now they're getting into the infrared, they're using violet light, right? When you start filtering with the different colors, what you're now doing is you're opening up the window of the electromagnetic spectrum in which you can see. So it's like as if you were running around observing the universe through a straw, and then so you're looking through your visual light straw, and then somebody says, oh, hey, for Christmas, would you like an infrared straw? Oh, ta very much. You put that with that. Oh, now I'm getting a much different picture, and now I'm seeing more. And can I also give you an ultraviolet filter, an ultraviolet straw? You keep adding to that. Pretty soon your bundle gets big enough. You can now observe the same object in such a range of wavelengths that now you can start to learn more. You can start to tease details out and maybe gain a better understanding. So this is very great stuff. If we go to the next one, please, Chris. So this is interesting. Okay, the plasma detector on the Cassini spacecraft recorded. We'll see if we can get the.
Sorry, I got a technical glitch.
Technical glitch? Has something happened to Cassini?
Yeah. Something's happened to the program.
Do you think it's going to flash up or not?
Nope.
Okay.
Nope. You want to bear with me for a second? I'll get it up.
Okay, we'll go for a second on that. Has anybody been looking at the Cassini site? Can we put the lights up here? I'll just.
Yeah, I was on that
just up a touch there, please, Chuck, so we can. That's great, like that, Attila. Thank you.
Yeah. I was looking at exactly those shots just a couple of days ago. One of the things they mentioned was that band where they're seeing the storm, and they started to refer to as Lightning Alley.
Oh, that's a good point. Good point. Yes, he's just saying that the band area where they're seeing that storm, they're now referring to that as Lightning Alley. Lightning Alley. Has anybody else been looking at the Cassini site? There's lots of interesting stuff going on there. I've got another image to show you on that.
Sorry, I got the same problem again.
Okay, so what we'll do is we'll leave that
online here.
Yeah, are you going to try it online?
Try it. Here you are.
This is the screen. Okay, so
there should be an audio.
So we're not getting.
Sorry, start that again.
So the sound of lightning on Saturn. Do you remember a number of years ago, John Thompson gave a presentation on the Aurora, and he had the sound of it. He had sound recordings of that, and he had all these different, I can't even remember all the terms. They had like chirps and beetles and all these funny little terms for the different types of sounds, whistles, and that came up from it. That's the second time I've actually heard sound now coming back from space. Okay, good work on that, Chris. Thank you very much. That was excellent. All right, now here on Saturn's moon Enceladus, what they were looking at was they had noticed there were these plumes of dust, but also gas jets. So what Cassini did was it looked across the plumes, and it needed something to, in a sense, to illuminate these plumes to see, are they actually coinciding? Are the gas jets and the plumes and the dust plumes coinciding? And in fact, they are. We'll go to the next image, and this is how they did it. Okay, this is back from 2003, and I think, when was 28 Sagittarii? When was that occultation? 89 or something, or 88?
88.
88, okay. In 1988, I remember this was one of the first things I ever saw, the first thing I saw Rob Dick present on, was the occultation of a star, number 28 star in Sagittarius, so we call it 28 Sagittarii, using the genitive form of the constellation name. And what happened is, you have the background star, and Saturn appears to move across in front of the star. Well, when it did that, and as happened again in 2003, okay, they're showing the star moving across this way. Actually, what you're viewing is the planet moving across that way. But when you have a much distant star in the background behind this planet, as the planet comes across it, as soon as the rings touch the starlight, something happens to the starlight. It dims. And it's going to dim by a certain amount depending on how thick the material in that exact section of the ring is. So what they could do is get a light profile up and down for every step of the way through the rings, until finally the star disappeared, was occulted by the sphere of the planet, and until it reappeared or emerged, and it came through. We could see the starlight right here in its full brilliance, and then again its light diminished by how much, and they could get an idea of what the density of the rings was. It was a stellar work, we could say. So this is what Cassini did. Cassini used the star Zeta Orionis. And if you remember, Zeta is, well, here's the main pattern of the constellation of Orion, the hunter. There's Betelgeuse, there's Rigel, and there's the 3 belt stars. It's 3 in a row on 1050 chum radio, right? The leftmost belt star is Zeta Orionis, and just underneath here is where the Horsehead Nebula is. There's Zeta. The other 2 belt stars are here and here. Okay, so there's Zeta. Here it is here. There's the Flame Nebula. There's the Horsehead Nebula. Cassini used that star as the lamp in the background. So, and it positioned itself so that as a star, Cassini lined up the star in the background with the plumes of dust and the gas jets, and backlit them, and that's how they could see them. That's how the instrumentation could see that and do the comparison. But if you go back to the next slide now again, notice they were using this star. Well, in my nice right-angled, well, not right-angled, but a sharp turn in the ecliptic, this is the apparent path of the sun and planets against the background stars. The ecliptic, the plane of the solar system, is on this level up here. So we can tell that to use Zeta Orionis as the background star to illuminate those features on Enceladus, it had to be somewhere else in space. It couldn't have been on Earth, because we don't have that vantage point. We can't see it there, because we can't see anything being occulted down this way. We can't get, because all the planets would stay along a band, something like this, along the band of the ecliptic. Right? Which also explains, I mean, this is, if you were to take your model of the solar system, build it on the kitchen table, got the sun in the center, got all the planets more or less all going around on the same table surface. Our Earth is tipped back 23.5 degrees on its axis. We don't see that, but we see it on the sky. We see the plane of the ecliptic tipped up. Right? It's not us that's crooked, it's everything else. So there's the table surface tipped up. So this also explains why we would never see, if we were to look at the Big Dipper, like where M81, M82 are, you'd never see a planet up there because it's too far above the plane of the ecliptic. All right, just thought I would pass that on to you. Okay, Attila, you going to talk about this?
Okay.
Good.
Observing is hard. It takes a considerable amount of self-control to focus your perception to see things that are basically at the limit of visibility. And even though photographs make it easy to see, it can be very, very satisfying to struggle to see something at the limit of perception. So it's a challenge for me to try to come up with an observing challenge, knowing that the people out there have such a great variety of equipment, and equipment does make a difference. So I've tried to pick one object, but try to find 4 challenges in it. And one of the challenges I haven't succeeded in doing myself yet. The first challenge is to simply find M51, the Whirlpool Galaxy, but try using 7 by 35 millimeter binoculars. It's possible, but what you'll be looking for is one star in a star field, so you'll probably have to memorize or draw a star chart and locate it by dead reckoning. It's extremely unlikely that you'll see any nebulosity at all. But in doing so, you may get some appreciation for how good Messier and Méchain were in observers in the 18th century or 16th century?
It was 1700s. I goofed up on 1700s.
Okay, this is the Whirlpool Galaxy. It has the strongest, i.e. highest contrast spiral arms of any galaxy, and was first discovered in a 70-inch telescope by Lord Ross. So challenge number 2 is to observe the spiral structure in an 8-inch telescope. This is hard, but it's possible. I've done it twice, once from Ontario, and it's extremely satisfying and cool to make out the ghostly shape of the spiral arms. It's very neat. Well, the nice things about a galaxy like M33, which is only about, backyard stuff, mere 33 million light years away, is in a larger telescope, say 15, 16 inches, you can begin seeing deep sky objects inside an external galaxy. Hit the button. One of the more interesting ones I've been looking at is a large star-forming region, I guess the equivalent of Eta Carina in our galaxy, which you can see circled there. This is a challenge to see because if you look at M51 in a moderate aperture telescope, you'll see what appears to be a number of feet of stars in front of the galaxy. And they are stars of the Milky Way except for one. One is actually this large star-forming region in M51, which I haven't been able to see the nebulosity, but it may be possible to detect it. But you can certainly identify it from its position, although you may have to spiral arm hop to find it. And last time I took particular delight in abusing you with a 16th magnitude galaxy, so I'm going to do that again. So the main challenge is IC 4278. This galaxy is probably further than 500 million light years away. It's actually a very nice, compact, barred spiral galaxy. It's difficult to find because there are a number of stars in the vicinity of approximately the same magnitude as 16, and this galaxy probably require a 24 to 25 inch telescope. And before you say that's completely ridiculous, who has a 24 or 25 inch telescope, you've just been invited to Rob Dick's open house. He's got a 24 inch, so you can bug him to look at this. Also, next time I'm observing with my 25 inch, I'll post to the RASC email list, and you guys are welcome to come out and try to see this thing. M51 is overhead at the zenith, pretty close at midnight, which means that this is a perfect time to try difficult to see objects like this, because you're looking through a minimum amount of atmosphere and the sky will be at its maximum darkness. So this is really the best time of the year. And the last challenge, this is the one that I wasn't able to succeed at. Next slide, please. If you zoom in here, you can see the nice bar in the 4278 over here on the left. But challenge number 4 is the bridge between the two components of M51. You can just see the edge of the big disk at the bottom right there, and the smaller galaxy. By the way, the reason why there's strong spiral arm structure in M51 is because these two galaxies are interacting. All spirals appear to have been caused by strong interaction. Many observers note that this bridge is very difficult to see, but this challenge is special. This challenge requires planning. You need about 6 months lead notice to make a reservation at McDonald Observatory to look through. I do mean look through, because they will put an eyepiece into their 82-inch telescope so you can look at the bridge connecting NGC 5194, that's the big galaxy at the bottom, to NGC 5195, the big galaxy at top, the two components of M51. And you'll be able to see star-forming regions in this otherwise nearly invisible arm that connects the two galaxies together. Actually, it's easy to see. The challenge is to not swear and yell at the top of your lungs continuously as you're looking through this eyepiece, saying things like, "Oh my God," for the 60 seconds or so it takes for the guy behind you in line to rip you off the eyepiece. I didn't succeed in that. I was jabbering for considerable length of time afterwards. It's a once-in-a-lifetime experience, but I think it would count as a great observing challenge.
Excellent. Yeah. There we go. So an Albert Sakely shot with Paul Commission's pick. So there's the galaxy. Paul, did you want to say anything about that, or we're just going to...
No, there's not much. The nice part of it is that it's face on. And this is where you can test your CCD or your eyes as to being able to distinguish between the bright arms and the dark spaces between.
So this is M101. And about 27 million light years away. And where you're going to find this one, we were playing around in the area of the Ursa Major. Yep. What did I just say? Yeah. Right. Yeah. So it's in the constellation of Ursa Major. We're looking at M81, M82 in the top part. We're looking at M51 just below the handle of the Big Dipper, and M101 is just off the end of the handle of the Big Dipper. So nice clustering, guys. Nice clustering. Right? Beautiful, beautiful galaxy to look at.
Very low surface brightness. Also, it's very bright there, but in a telescope, it's very. You can go. It's really easy in binoculars, and then you get a telescope there. and you could go right over it, you wouldn't even know you saw it.
Okay, Gary's making a very good point there that it's very low surface brightness. I mean, it looks like a blow 'em away one on the screen here, but remember that the light is so spread out, it's going to be quite dim. So let your eyes adapt. Use your averted vision. Use all the tricks that you've been reading about or been hearing about.
There's some star-forming regions there, just under where it's called Nave Commission. There's a little area there.
The star-forming regions here.
This is weird because this actually has NGC object numbers to those H2 regions. There's about 4 or 5 of them. There's
Right.
one.
So yeah, so as Gary's saying, so if you look these up, you'll see that they have their own NGC numbers, the new general catalog numbers. Excellent. Yes.
Regions are actually easier to see than the spirals.
Yes.
Yeah, the star form. Good point. The star forming regions are easier to see than the spiral arms.
Make sure that you actually see the core rather than the star-forming regions around it. I've seen people who have stopped once they found the outline of the star-forming.
Okay.
They didn't actually find the main galaxy.
Yeah, another good point. Now, see, this is the experience of observers coming through. They're saying, make sure that you see the core of it, and make sure that you haven't just seen the star-forming regions around, thinking, oh, that's the galaxy. Make sure that you can see what you can see. That's always the way. Paul, I've got your token here. I'll be down with it in just a second. Let's hit up the next. All right. So there are actually 2 lunar challenges. All right. So lunar challenge number 1: sketch and label the near side moon. I made it easy. I didn't say the far side moon. So, all right. So look, Rob Kaufman did a beautiful sketch. It's I think this one was done with an ink wash, which is very similar to what Galileo did. Galileo Galilei did an ink wash. A little bit more detail over here. Right now, about 8 years ago, a woman decided, she was an artist, she thought, well, she's seen all of Galileo's sketches and paintings of the moon. She thought, could she do the same thing with a very small telescope? Remember, he was using something like a little 16-power instrument. And so she used a very, very small instrument herself and then tried to see, could he actually have done that? And her images, I think if you can maybe get back in the archives of Sky and Tell, have a look at her very happy results on that. Okay, I've taken some stabs at going along and identifying features, just doing quick sketching. It's just for fun, just for my own edification. Here's another type of thing. What I'd like to see is if you can get as much as possible of the entire surface, sketch it in, throw some labels on, see what you can get. There'll be prizes for the best sketches of this for next month. Okay, that'll be different from just your token coming in and giving an observation, but there'll be prizes for the best lunar sketch, and no scanning anything out of a book. All right. Now, the second challenge is a bit different. This is taken, I believe, from the ISS, the International Space Station. Looking across the top of the Earth, there's the moon rising in the background. So the idea here is photograph the moon from altitude.
I hope it doesn't have to be quite that high, though.
Now, altitude. Let's face it. Chris Tarrant has more altitude than I have, right? So however you interpret altitude, okay, that'll be great. Let's see what you can bring in to the June meeting on June 6th. Now, what I'm hoping is some guy sitting up in the International Space Station is sitting there, not too much to do on a Friday afternoon. He's looking out the window, sees the moon coming up, and he goes, hey, I was just on the Ottawa RASC website. They're looking for something. You know what? Wouldn't that be something? Okay, so that's the challenge for there.
They'll send you up to give him the pin, eh?
Yeah. Oh yeah. Oh yeah. I'm there. I'll deliver the pin for sure. Okay.
6 months late.
All right. Now, just if we could, Chuck, could you bring the lights up a little bit, please? Are you right there? Thank you. Just a reminder that our next meeting is going to be. We've got the. Look at that. What timing? Okay. Our next meeting is going to be June 6th. Now, of course, June is the month of the summer solstice, and I'm thinking that we could have some fun with this as well. So the June meeting, in addition to the swap table, because we have a mid-year swap table, if you have items to sell or to trade, whatever you want to do, we'll be setting up the tables like we did in December. Bring your stuff down. But there'll be special prizes for people who play along with Brian on Dress Like a Druid Day. We're going to be New Agers, Druids, whatever it is. whatever it is, in costume, the best costume are going to have prizes. All right? Okay, there we go. Gary Boyle, thank you very much for doing the count again. 141 of us, I think, enjoyed ourselves here this evening. And on that point, could I just make a little note? I'm wearing my little medallion here. It's not a medallion, it's a little figure. It's the Speak No Evil. And just a reminder that in our room here, that we always try to create a welcoming environment to everybody who's in. And I think sometimes if comments get misplaced, then it sends people away feeling not so great. So whatever you can do to make everybody as welcome as possible in our group is the way to go. All right. So coffee and treats outside from Ann Fraser's already outside there. If you need membership information, Art Fraser's sitting right under the light, right there with his hand up. And we have Estelle Rother is going to be zipping out. She just finished recording this meeting, so she's doing all the recording. Estelle, are you popped out already?
No, it's still here.
You're still here. Are you still writing? Where are you? Oh, there you are. Okay. So Estelle has been recording for the last while all of the meetings. So when you see the recorder's notes in Astronotes, that's Estelle Rother. So thank you very much for doing that, Estelle. Estelle has also taken over as librarian from Richard Kixey, who's off playing daddy. I mean, what's that all about?
Paternity leave.
Paternity leave, yes. All right. So Estelle's dashing out right now. In about 5 minutes, she'll be set up to go just on the other side of this bulkhead here. If you can go out these doors, there's an office right there. That's where our book library is. All right? So June 6th, dress like a Druid Day. Thank you very much.
How did Druids dress?